SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We are in this topic of forced response. And we have been looking at response of specially cylindrical shells. Okay. Now, very often you will find that there is a panel which has a cylindrical shape, but it is not a full closed cylinder. Okay. So, it looks like this. So, it looks like this. It is a part of a cylinder which is not closed in the theta direction. Okay. And let us say it is simply supported here, here, also here and here. Okay. Then what do you do? Okay. So, now you have the same simply supported conditions at x equal to 0 and L. Okay. Your x equal to 0 is here, x equal to L is here. So, the conditions here are that of simple support which we have seen. Now, even this side is simply supported. Okay. Earlier, because of it was closed, there was a continuity condition. Okay. So, now this time there is no such continuity requirement. Okay. So, now what happens? Okay. So, what happens is you had to put simple support conditions here. Okay. So, that means what? The U3 at x. So, let us say this is x, okay, and that is theta. Okay. And let us say this total angle, let us say this total angle is gamma. Okay. And this radius is a, and let us say we are measuring theta from here. Okay. So, U3 at x comma theta equal to 0 comma t is 0. Okay. The radial, it is radially supported. Then Ux, okay, at x comma theta equal to 0 comma t is also 0. That means this displacement arrested at the edge. Then you have m theta theta x comma theta equal to 0 comma t is equal to 0. Okay. So, this moment is 0. Okay. It can't support the moment. Then n theta theta at x at theta equal to 0 comma t 0. So n theta theta is this normal force resultant, or yeah, normal force resultant born out of sigma theta theta. Similarly, the other edge you have u3 x comma gamma comma t equal to 0, then ux, okay. So u3 is 0 over here, then ux, this ux at x comma gamma comma t is 0, and m theta theta x comma gamma comma t is equal to 0. Okay, so this moment is equal to 0, and then n theta theta at x comma gamma comma t equal to 0. So n theta theta is again the normal force resultant. Okay. So now, so the modes, what shape, what mode shapes, what are the mode shapes that satisfy these conditions? Okay, so they are ux x comma theta is a cos m pi x by L sin n pi theta by gamma. Okay, then u theta x comma theta is b sin m pi x by L cos n pi theta by gamma. And u3 x comma theta is c sin m pi x over L sin n pi theta over gamma. Okay. Now if you substitute this into the cylindrical shell equations, okay, so that means what? The general equations with A1 is 1, A2 is equal to A, let us say that is the radius A, then R1 is equal to infinity and R2 is A. Okay. In the general set, if you substitute this, you get cylindrical equations. Into that you substitute these mode shapes. Okay. Then you get, as before, a matrix, okay, rho h omega square minus k11, k12, k13. I am just taking it out from the text. Then k21 rho h omega square minus k22, k23, then k31, k32 rho h omega square minus k33, A B C equal to 0. Okay, so for a non-trivial value of A B C, if this 0 has to hold, then this has to be singular, that gives you the resonances. As before, you will have 3 sets as for the closed cylinder. Okay. Now just some listing of expressions. K11 is equal to K times m pi by L whole squared plus 1 minus mu by 2 n pi by a gamma whole squared then K12 is equal to mu K by A m pi by L. K22 is equal to K plus D over A square into 1 minus mu by 2 m pi by L whole squared plus n pi by A gamma whole squared if you have the text, then these are there in the text. In case you don't have the text, this is the expression plus D over A n pi by A gamma m pi by L squared plus n pi by A gamma whole squared, and that is also equal to K32. And D is the bending stiffness, okay, E h cube by 12 into 1 minus mu square. Okay. And K31 is mu K by A m pi by L is equal to K13, and K33 is equal to D m pi by L whole squared plus n pi by A gamma whole squared plus K by A squared, and K is the membrane stiffness. Okay. So with this set of values, you can go ahead and compute your resonances. And mode shapes. And as before, this whole thing together is a mode shape. That's important. Okay, this set of amplitudes and this set of shapes together is one mode shape. Each of these is not one mode shape. This together is one mode shape. Okay, so the A value, B value, C value are related at every mn end n for that particular omega mn. That is a mode shape. So you can get the resonances and mode shapes. Okay. Now after this, without so much elaboration, just as we have done before, you can compute the forced response. Okay. So I will not, you can have a panel and you can have a force, then you can have a q3 x comma theta comma t, okay, and then from you get your fmn, from there you get your gamma tilde mn, there you get your eta mn, and then multiply by the mode shape. So you get your w, which is a summation, etc. Okay. So with this I close the forced response section. Okay. Forced response section. So the next topic we are going to look at, is connected systems. Connected systems. Okay. What do I mean by connected systems? Let us say I have a beam. Let us say I have a cantilever beam. Okay. I know its mode shapes and resonances, etc. But now it is connected to a spring. One end of the spring is grounded, the other end connects to some point on the beam. Okay. So how to do that? How to do this connection, or how to find the new mode shapes, and natural frequencies. Okay. The potential of this method is huge. Okay. The method now is called the receptance method. So what is this receptance method? What is receptance? Okay. So receptance essentially is denoted by alpha ij, is we will call it the displacement response at a point I for a unit force applied at point j. Okay. And this force is harmonic. These are defined at single frequencies. Okay. Now suppose, so we will take an example now here. Suppose I have a system A. I have a system A and a point 1, and I have another system B and the point 1 on B. Okay. So they are connected through a single displacement. Okay. Then what happens? Then what happens is this. There is a force that A experiences, let us call it FA1 given by capital FA1 e to the power j omega t, okay, and there is a displacement it experiences which is small x a1, which is capital X a1 e to the power j omega t. That means we cut the connection and look at A freely. Similarly, the point 1 on B experiences a force which is FB1, which is equal to amplitude e to the power j omega t, and a displacement which is small x b1, which is equal to capital X b1 e to the power of j omega t. Okay. So now we will define the receptance for system 1 or system A. Okay, so system A, which has alpha ij receptances. Okay, so the alpha 11 is small x a1 by small f a1, which ends up as capital X a1 by capital F a1. Okay. Then system B is defined by beta ij receptances, okay, and beta 11 is equal to small x b1 by small f b1, which is equal to capital X b1 by capital F b1. Okay, so that's what is happening within each system, but now they are connected, they are connected through a unidirectional displacement component. They are connected. Okay, so now what does that mean? That means that x a1 must be equal to x b1. Okay, x a1 must be equal to x b1. Okay, so this is equal to what? X a1 by f b1. Okay, what is the other one? The other is, these are internal forces now. So fa1 must be equal to minus fb1. So this force here is now internal. Okay, as A forces B, B will force A back. Okay, so these are internal forces. So fa1 is equal to minus fb1. So this is what xa1, and fb1 is minus fa1, but xa1 by fa1 is alpha 11. So xa1 by minus fa1 is minus alpha 11, but that is beta 11, right, which means what? Alpha 11 plus beta 11 must be equal to 0. Okay, so this is a very important equation. This is the equation which will give you the new natural frequencies, and from there the mode shapes. Okay, so to start it off, let us take first example. Okay, example is that of a rectangular simply supported plate connected to a spring, connected to a spring. So let us see what we have here. What we have here is a plate here, simply supported on all edges, and then we have a connection with a spring. Let us say the spring constant is K, the other end is grounded. Okay. So now there are two systems. Okay, the plate forms system A, let us say, okay, and the spring forms system B. Okay, and this is a one directional connection. It's a vertical connect. That's the connection. Vertical displacement connection. Okay, so now we want, for A we want alpha 1 1. Okay, so let us say this point is x star comma y star. Okay, so this is my x, that is my y, that is my z, and this is x star comma y star. So okay, so you want alpha 1 1. Okay, so in order to do that, what is Q3 now? If a force is applied at x star y star on system A, so let us say F is the force, then delta x minus x star, all these we have seen now. Okay, so I will not elaborate again. Okay, so then because it is harmonic, my Fmn star is 1 over rho h nmn integral 0 to A integral 0 to B f delta x minus x star delta y minus y star sin m pi x by A sin n pi y by B dx dy. Okay, this gives me 4 by rho h a b f sin m pi x star by A sin n pi y star by B. Okay, so now what is gamma tilde mn? Gamma tilde mn is 4 by rho h a b f sin m pi x star by A sin n pi y star by B into the frequency term where we do not include damping now. Okay, omega square mn minus omega square. We do not use damping here because we want mode shapes and resonances. Okay, we are not looking at responses, we are looking at deriving mode shapes and resonances. That is the objective. Okay, so then the rest is as before. Eta mn is gamma tilde mn e to the power of j omega t, and further you can get the response w x comma y comma t, which is, I will write w x comma y comma t is equal to summation and summation 4 by rho h a b f sin m pi x star by A sin n pi y star by B divided by omega square mn minus omega square and the mode shape sin m pi x by a sin n pi y by b e to the power of j omega t. Okay. So, that is the response, which is small x a1, let us say. Then we have the force. Okay, we have the force. So, what is alpha 11 now? Alpha 11 is summation. So, this is m summation is n. So, summation over m, summation over n, 4 by rho h a b. So, force is applied here. This is the general response. I want a response also where the force is applied. So, this gets a star and star as well. So, I have sin square m pi x star by a sin square n pi y star by b, and the frequency term 1 by omega square mn minus omega square. Okay. Now what? Now the B system. Now the B system. Okay, what happens to the B system? The B system is this. There is a force applied. Okay, F B1, which is F B1 e to the power j omega t. Okay, and that results in a response which is x b1 e to the power of j omega t. Okay, that is given by what? F b1 e to the power of j omega t by k is equal to x b1 e to the power of j omega t. If that goes, x b1 by f b1 is 1 by k. So, that is beta 1 1. Okay. So, now the equation is, what is the equation for new resonances? Alpha 1 1 plus beta 1 1 is 0. Okay. And therefore, double sum mn 4 by rho h a b sin m pi x star by a squared sin n pi y star by b squared by omega square mn minus omega squared plus 1 over k equal to 0. Okay. Now, what happens next? If I, so this is a positive quantity, this is a positive quantity, this is a positive quantity, okay, and this goes positive, negative. So, if I just write a few terms separately of these, there is something on top which is positive, and I have omega 1 1 square minus omega square. I have something positive. I have omega, let us say 1 2 square minus omega square, and I have something else positive, omega, let us say 2 1 square minus omega square, then one more term, some positive thing on top, omega 2 2 square minus omega square, and so on, plus 1 by k equal to 0. So, let us look at each of these terms. Okay, so what happens? Or rather, this sum looked at in this manner, what happens? We plot this. Let us say this is omega 1 1, this is omega 1 2, this is omega 1 3, this is omega 1 4. Okay, and I am sweeping omega, that is the idea. Okay, this independent axis is omega, I am sweeping omega frequency. So, till omega reaches omega 1 1, this is a positive term, and as omega reaches omega 1 1 from below, it goes to positive infinity. So, let us see. So, this goes to positive infinity. Okay. Then it, as soon as omega crosses omega 1 1, it goes to negative infinity. Okay. And then somewhere it goes to 0 because of these two terms. And then as omega starts to approach from below again, because omega 1 2 is higher, omega 2 1 is further higher, that is the assumption. Okay. So, now it goes to positive infinity again. Then just as it crosses omega 1 2, it is negative infinity, and then it goes to, so this continues. So, the summation term looks like this. Okay. So, this term or these terms together, they look like that, and they must be equal to minus 1 by k. So, let us say minus 1 by k, k is a constant. So, this, if we plot that, it is minus 1 by k like this. Okay. So, where are they equal? They are equal, the two are equal here, 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 and so on, they are equal. Okay. So, now what? These are the new resonances. These are the new resonances. This is the new resonance. This is the new resonance. Okay. So, you can also see that every resonance is raised, or every natural frequency increased. Okay. Why? Because we stiffened the shell or stiffened the plate. Stiffening effect of the spring. Okay. So, let us say now we have found the new resonances. So, we have omega 1 new, omega 2 new, omega 3 new. Graphically or numerically we can find that, the new resonances, right, these values. Okay. Then what is the new mode shape? What is the new mode shape of the plate? Or how would you find the new mode shape? Okay. So, the new mode shape at a resonance at a natural frequency, the response is dominated by the mode shape, right. At a resonance frequency, the shape of the system is the mode shape. So, if I have omega 1 nu as a new resonance and I substitute that over here, omega equal to omega 1 nu, then this is the response of the new system at the new resonance, and therefore that is the mode shape. Okay. So, the mode shapes of the plate that is stiffened by a spring at a point are these: double sum Mn 4 by rho HAB sin m pi x star by A sin n pi y star by B sin m pi x by A sin n pi y by B divided by omega square Mn minus omega I nu squared, I going from 1 to etc. So, these are the old resonances of the plate, okay, and the new resonance is a weighted sum of the old mode shapes. So, analytically we have analytical new modes. It is a very powerful technique. Okay. We will do for a higher order system in the next class. I will close here. Thank you.